Hello everyone, my name is Gary Kotzur and I'm Marvell's storage CTO. And today we're going to talk about memory and storage controllers that are optimized for the data center. So the first one we're going to talk about is NVMe storage, and we're going to touch upon a few key points around this technology, and then we'll transfer over to the memory domain, talk about CXL. So let's go and get started. So what is cloud storage? I think the first thing we want to do is look at what is common about cloud storage. So there are common goals such as performance, reliability, security, as well as robustness. So where we get into differences is that everybody has their own idea about cloud and storage. They have their own vision, and they also have their own implementations for that vision. So some of the areas that they look at are, what are the use of standards, what is open initiatives, and then also too, it could even be proprietary. So whenever you combine this together, what we're seeing is that we have customers in the cloud space that we have to be able to meet all their different needs. So what this means is that for the silicon architect, we have to come up with architectures that are flexible to be handled in a varying array of systems that are easily configurable and also can be optimized. So what is necessary to be successful for a silicon supplier? So when we look at the technology, we need to have leading edge process nodes that can provide the lowest power and the highest performance. We need a management firmware that is optimal and robust. And we also need to be able to provide high-speed PHYs. And of course, we need to be able to have technology to support the different types of virtualization, whether that be hypervisors or containers. And of course, security is very important. And we can also say that high performance is also key. So a flexible architecture can be applied to either a SSD controller or an accelerator, or even for a converter, in this case, from NVMe to NVMe over Fabric. Let's talk about enablement. So what we need for these different types of solutions are silicon that can range from either merchant all the way to custom. We can have firmware that ranges from a reference design to production. And then likewise, we need to have validation that supports different levels from quality, reliability, as well as interoperability itself. So whenever the industry started working on SSDs initially, everybody was concerned about performance, but what we're hearing from our customers more recently is they don't want just high performance, they want solutions that are also low power and they're also economical to operate. So whenever you look at the different use models, we can look at low power is needed for the cloud edge, as well as those types of environments that are power or cooling constrained. And then likewise, we still need that high performance because we do have many use models in the data centers for high speed performance. Another area that is important is quality of service in multi-tenant environments and also in virtualization. So in this example here, we show an SSD controller that can handle multiple tenants concurrently and protect the data from each of the different tenants themselves. Now you could do this inside the SSD controller itself, or you could actually put it inside of an accelerator that sits between the host and the host OS and the SSDs. So you can accomplish this one of two ways. So let's talk about the security aspect. What we're hearing from our customers is that this is becoming one of their dominant concerns and the data center. And so whenever you look at the different types of ransomware and the hacking that goes on, there's a big concern around it. And so what we aim to do is to be able to support the latest threats, protect against the latest threats, not support them, as well as the latest standards around security. So today, for encryption, you have PCIe, NVMe, and of course, CXL. And then for the storage standards, you have DMTF, TCG, confidential computing, and then as well, of course, you have OCP. So we're going to move from the storage domain now to the memory domain and talk more about the different ways that we can leverage the expertise that has been developed for NVMe and utilize it for CXL. So when we look at the cloud environment, what is common is that you have virtualization, you have multi-tenant, as well as SDS. For PCIe, starting with PCI Gen 5, and we're moving to PCI Gen 6 in the near future, and of course, future generations of PCIe. Now for capabilities, we have, of course, the flexibility, the management, also the QoS that also has to be, that is common between the two different domains. Also are the goals itself. So in both cases, for NVMe and for CXL, what's important is, the low power, lower latency, as well as lower cost, as well as higher performance, higher capacity, as well as high availability. So let's talk about the ecosystem. The ecosystem is composed of the industry itself, which is the customers, the vendors, the standard bodies, as well as the open initiatives. And last is topology and enablement, all the way from a standalone server to a composable infrastructure that can handle all the different types of applications that are out there. So the first use case for CXL that a lot of people talk about is memory expansion. And today, in this example, what we're showing is that performance doesn't always scale with additional capacity. So if you go from 1 DIMM per channel to 2 DIMMs per channel, the 2 DIMMs on that one channel are sharing the bandwidth, so your performance does not increase and your performance is going to end up being capped. In the future, instead of using the 2 DIMM per channel approach, we will instead be able to add CXL memory expanders, which will allow you to have increased capacity and increased performance, because we have scalable performance due to the PCIe lanes opening up the memory bandwidth. Next is we'll talk about sharing resources with CXL. So today, when a server is provisioned with memory, they provision it to handle the most intensive workload. But the problem with that is that as the workloads vary, that memory cannot be shared, or I should say, cannot be rebalanced, and you end up with inefficient memory utilization. With CXL pooling, you'll have either CPUs or even processors that can actually share this memory, and they can actually rebalance it across the different nodes or CPUs, depending upon the varying workloads. And this allows lower memory requirements, thereby saving overall cost inside of a system. So let's move over to CXL switching. So just like before with the sharing, we're able to now share the different resources and improve the overall utilization. So in this case, we can rebalance our resource utilization for different devices such as I/O, accelerators, or even memory expanders. And this allows scalable performance as well as even serviceability in some cases. So next is about accelerating CXL. The DIMM itself is not an optimal environment to add offload capabilities, but with the bigger footprint with a CXL device, we were able to add sufficient acceleration, which allows us to provide offload capability. And thereby, we can improve the overall TCO of that system. Likewise, when we have coherent caching capability, we can further accelerate the different devices themselves, whether that be DPUs, or NICs, or even SSDs. And this also provides composability for the I/O devices. So here's a quick summary of how CXL solves the different data center memory challenges. You know, we started with having memory that is tied to the CPUs. Now with CXL, we can have disaggregated memory that is fully composable. This allows, again, sharing of the memory, sharing of the different resources, thereby bringing better utilization of both of the memory and the different resources themselves, as I mentioned before, such as accelerators and I/O devices. Next is the bandwidth per core that is declining. So in this case, we're moving from, you know, again, the two DIMMs per channel to adding CXL memory devices, and that optimizes our efficiency overall. Next, going from not being able to offload data computation to near memory computation by having accelerators that are built into the cards themselves. Next, let's talk about the overall vision. So today we have shared nothing servers that are connected by Ethernet, and this has done a good job for quite a while, but with CXL we can improve upon it by extending the resources used by a server out into an appliance, whether that be for extended memory or additional resources such as accelerators or even I/O devices. We can improve the overall capability. And then last, in the future, we'll be able to have everything disaggregated, the compute, the I/O, the memory, as well as the storage, and they're all hooked together by CXL, which is a low latency bus, and that realizes the full composability solution that has been desired with CXL. So let's talk about how Marvell is uniquely qualified to handle these types of solutions. So with silicon leadership, we have made a huge investment in 5 nanometer technology, and we're already starting on the transition to 3 nanometer. We have internal development for both our PHYs as well as our IP. And then next is our firmware. We can handle any level of firmware development that is desired, from an SDK all the way to production. Today we have existing partnerships with our memory vendors, both DRAM and NAND. And then last, we have a huge investment also in the ecosystem in ensuring that our solutions work on all platforms. So whether your needs are going to be for memory or for storage, Marvell can Marvell can help you realize your overall goals. So anyway, I want to thank you all for your time, and that concludes. Thank you.